Hello, hello. Can you hear me? So, this is the weekly tutorial live for Houdini, which is titled as Houdini Algorithmic Life, and this is the 105th episode for that series. And this is Junichiro Horikawa, and I would love to start live. Right now, this is 3:30 a.m. in Japan time, so it's pretty late. I believe most of the people in Japan are sleeping right now. But since tomorrow is holiday, that I forgot what's the day was it? What's the holiday's name? But it's holiday in Japan, so I guess I could do a late night live stream. All right. So the topic that I chose to do today is pretty simple. It's I title it as an energy field, but it's just a simple noise-based particle animation, which is repeatable, so procedurally controllable, um, using your desired frames. So I guess it's suitable for, like, I don't know, GIF animations or GIF animations, or could be ported to could be exported to like game engines to use it for effects or something like that. So and the setup could be used on top of any geometries. For example, sphere. Sorry that it took a little bit of time to update. Yeah. So running the particle animations on sphere is still repeatable, loopable. Could also work on more complex geometry like big head. It still looks nice. Also repeatable, using just a simple noise function to achieve this. And there are several parameters that I could change. For example, the repeatability, the size of the noise for, since I'm using a periodic noise, the size of the periodic noise, or the size of how much spread you get with these particles, or to color these particle, I am also controlling the density based on the distance, the search distance. If the particles are close enough, then you have high density. If particles are far away, then you have less density, and then I am coloring those particles with those density values. That's kind of a reason why the setup is a bit slow, because of these density searching. So without these, you could run it a bit faster. But the visual looks nice, so I am including it. Okay, so that's what I'm gonna do today, and I don't think it's gonna take much time to finish this because it's pretty simple. Alright, so let's see how I did this. Let me just bring this up to the above. Alright. So it's just kind of a playtime for me, playing around, messing around with the geometry. Okay, so let's try with a simple geometry first, something like grid. So I'm gonna create a energy field on top of this flat grid surface. Okay, I'm also going to create a switch so that later I can switch the geometry. Now, first thing first, I am going to create, probably I would like to move the points on top of the particles on top of these surfaces, so I am going to create a bunch of points on top of it using a scatter node. So I guess one of the parameters you would like to set is the number of points you want to use. So let's create a null node, which I'm going to store all the parameters that I would like to use, as always. And let's create two parameters. One is the type of shape you want to use as a base, and one is the number of particles. Let's say how many points is maximum? 100,000 probably, or a million, I don't know. Okay. I guess that's enough for So the shape, I only have one shape, so 0 is fine. I'm gonna copy the value to this switch. And the number of particles, let's say I would like to try like 500,000 something. Large enough numbers. Alright, so you are filling the grid with all those points. Maybe that's too much for testing, so I'm gonna make it 50,000 for now. And let me also save this to the today's folder. Now, I also would like to apply a normal direction to each of the points based on the attached surface. So I'm going to create a normal node just before creating a scattered points. So something here based on the points. All right. So now each point has these normal direction, which I am going to use it as a direction to move as an energy field using the noise related value. Okay. Now it's time to move the points. I'm going to use the point wrangle. Let's name this energy field. Okay, so let's think about what kind of stuff we need to do. First of all, since I would like to create the animation for energy field, and I also want to make it repeatable, so meaning right after I hit the end frame and go back to the first frame, I would like to smoothly connect the result of the end frame to the first frame. Okay, so in order to do that, you do need to have some kind of a value which is seamless, and I also would like to use noise function. So with those conditions, one of the options that I have is to use a periodic noise. And if you go to the Vex functions documentation page, you have this p noise, which is used to create a periodic noise. Okay, and you can use this to have a repeatable or seamless noise functions, and as you can see, you have 1 or 3 or 4 parameters, 4 vector values parameters to be able to use as a seed. And I think I would like to use the last parameter set for this P noise because I can use X, Y, Z as a position and T as a time. So in this case, these frame value. Okay. So right after I hit the 240, then come back to 1. I can set the limitation or I can set the duration of these frames as PT, which defines what's the range of this periodic noise for each X, Y, and Z. Okay, and PT could be used to define the range for the time step or the frame number. Okay, so keep that in mind and let's try to use that. First thing first, I would like to create a seed value. Okay, since what I want to do is to use a point position and the time. So let's create those value first. So I'm going to create a variable called positions derived from a position, right? And I also would like to create the time-based value, which is frame. Okay. And in order to make this repeatable, I would like to kind of normalize these frame value, first of all, to 0 to 1, so that it will be easier to use. So I am going to divide this with the $f_end, which stands for the end frame value, in this case 240. So as a result, you get the value in between 0 to 1. Now, not exactly 0 because it's starting from 1. So if you specifically want the value from 0 to 1, then you do need to make this subtract by 1, but it's okay with these for now because you want to make it periodic. You do have some gap between the end and the first. If you make both becomes 0 and 240, then that means you are going to get double. I mean, you're going to get the same value on the end and the first frame. So there's going to be a glitch when you goes from the end frame to the first frame. So you don't want that, so that this is actually fine. Okay, now the next thing you want to do is to multiply this by a range of or the speed, how fast you want to move the frame. Okay, and that I think it should be based on the actually it could be any integer value, because in order to use a periodic noise you have to use an integer as written here. Okay, it says integer here, which indicates how many like repeated patterns you have in these directions X, Y, Z, and T. And the one that I want to control for the time step is for PT, and the integer meaning is that how many repeatable pattern you get in these time step. So if you use 1, then you are only going to get one repeated pattern, meaning every step is unique from 0 to 1. Then but 1 and the value on the step frame 0 and the value at the end frame is the same. But if you make it 3 or 4, then you have 3 same patterns during these frames. So if you have 4, you have 1, 2, 3, 4 noise patterns, which moves exactly the same. Okay, so more pattern, more integer value, more pattern you get, I mean the larger value you use, faster you get, and repeated patterns you, more repeated pattern you get. Okay, so let's create the variable called speed. I'll call it speed as an integer value. And multiply it with these frame state value, which is in between 0 to 1. So if you multiply by speed, what you get is, if you say speed is 5, then the value will become 0 to 5. Okay. Now it's time to use a p noise, actually. So noise, or well, how would I say? Force is equal to p noise. Now you have 5 parameters. One is the vector 4, and rest is the number of repeated patterns on these directions. So I guess you also need how many repeated patterns you want on X, Y, and Z, and that could be, probably that could be the same value, I think. So let's try to make that. And these repeated patterns are actually based on the actual size of the coordinate. So 1 means if you set 1 to px, then that means the pattern will be repeated on when the x goes over 1. For example, if this is the x-axis, you have one pattern here, one pattern here, one pattern here if ptx is 1. If this value here, if px is equal to 2, then you get one pattern here, one pattern here per 2 coordinate. So larger the value is, you get bigger scaled, larger scaled pattern. Okay, so you might want to control this based on the size of your original geometry. Okay, so it makes sense to make it parameterized. So I'm gonna call it size, or noise size, I guess. I'll just call it n size, and that is also integer. Just call it size. All right, now's the time to create a vector 4 value, which is this one, including your position, point position, plus t. So let's create that. I'm gonna call it seed, and just copy the x, y, and z value. And for px, py, pz, I'm just going to use n size, and n size, right? And for the last, wait a minute, what did I, oops, no. What I wanted to make is just a vector 4, so the last value will be this t. Okay. All right. Now I have created the vector 4 value. Let's apply it here, and px, py, pz is n size, n size, n size, and the last value will be speed, based on the time. All right. Okay, so hopefully this will do something. And now that I have this value, now that I have this vector value, let me see. So the output is vector, which is probably in between 0 to 1 for all x, y, and z. So let's try to use that to move the point, actually. So And since I want to make it possible to move on the negative direction as well, I am going to subtract this by 0.5 for all x, y, and z, so that the range will become minus 0.5 to positive 0.5 for all x, y, and z. Alright. Now that I have this force value, let's try to move the point, shall we? So, in order to move the point, we just add this force with some kind of size multiplication. So let's define some additional parameter to define how far you want to move the point. So how do I call this? Strength. Okay. Now currently it's 0 and the size is 0, so let's make it like 10 and see what happens. If I increase the size, you start to see some noise pattern happening. Alright. Nice. Let me increase the range, the strengths to 10 and size to 100. And tries to look for the best value. Now, interestingly enough, if you increase the size, the pattern is changing. And this part is not changing after like 2 or 3. That is because of the size of this grid. This is the seam line, seam edge for this pattern. So it's changing this one, and this one, and this one, and this one always starts from the left top corner, so it's not really changing even if you change these sizes, but that's okay, it's still seamless as you can see here. Okay, if you change the size of this grid, something bigger, so it still remains seamless, so that's fine, looks fine. Okay, now it already looks okay now. I mean, these are colored in all white, so you don't really see, doesn't really look like an energy field yet, but actually the geometry itself is this. The output that I wanted to create is just this, so it's pretty simple in terms of the output. If you play it, you start to see some noise field dancing, and the point is when it comes from end to the first frame, it just repeats. So that's what I wanted. And let's try this out with other geometry to see if this still works. Something like pig head. Change the input to pig head, and maybe I would like to make the pig head size a bit bigger. And still seem to work. Okay, so that's good. And let's also increase the number of points to 500,000. And still fast enough because there's not much calculation going on here, it's just moving the points procedurally. Right? And you could control these densities or the size of these noise by going into well, actually I have to do something else in order to change the density of these field. So in order to do that, you just need to, I don't know, scale the original surface, because you can only use integer on periodic noise. The size is kind of defined by these sizes. So the size of the original geometry is kind of pretty important in order to control the size of these field. If you make it 20 by 20, you have more density in terms of the field. If you make it 5 by 5 smaller, you have a big gesture like these. Okay, well, I'm gonna keep it with 10 by 10 for now and see how this will. And you could also use the normal direction value to kind of amplify the directional force to those normal direction. In this case, the normal direction is always going upward, like that. So let's say I want to amplify these noise value based on those normal direction. Okay, so let's think how we can do that. So this is the force field, and what you could do is to get the y component or the normal directional component of this force, then multiply that direction, in this case just the y normal direction, but let's say it's you don't know which direction the normal is heading to, so you're going to guess what's the component of that direction with this force strength or force distance. Then you want to multiply that value by some kind of parameter, then add it together to the original force value. So let's think about that. That means you just want to scale this force to that direction, right? So how do we do that? One way you could do is to first of all orient these force field to the x or y or z direction, then it will be easier to uniformly scale to a specific axis. You just need to multiply x, y, or z. Or you could get the x, y, and z component or distance when projected on top of the normal direction, and using those values to scale x, y, z value of this force one by one. Let's try that method, shall we? I haven't tried that myself, but could be interesting. Alright, so let's think how we could do that. Let me make this as a force yet, not being added to the points yet. Now, what we have as a normal direction is at n, right? And what I would like to do here, in terms of the scaling, is first of all deconstruct this normal vector into x, y, and z direction. Right? So let's do this. That's, well, the thing that I'm trying to do here might not be smart at all. It's pretty dirty implementation, but let's see. I mean, it's still fun. So what I mean is just get get just the x component of this normal direction and use it as a x-axis value, x-axis vector with some size. Although we know that the normal direction is y direction, so we know that this value is 0, but let's assume this could be some random value. Another normal direction set. We have y component and we have z component. Like that, right? So we have 3 vector value in x, y, and z coordinate, and by adding all those 3 vectors, you get normal. Simple. Now, the reason why I have deconstructed these normals into 3 is to calculate or project this force onto these normal direction in order to calculate the size. Okay, so what I mean is, what I wanted to do is calculate and probably I should make these force as a normal vector value in order to uniformly calculate the value. So I'm gonna make this as a normal value. Okay, and I am going to calculate the dot product between x norm between the normalized force, y norm between the normalized force, and so on. And as a result, you get projected value of these x, y, and z onto the force. Okay, which means you get how much size you need in order to what axis is dominant in order to control scale force. I think, is it? Yeah, because each one has different size, right? So let's try out. I mean, it's just a hypothesis, so I don't know if it's gonna work. So dot x, the dot product between the normalized force and the x norm. Do the same for y and z. Starting to get geometrical, isn't it? Okay, now that I have dot x, dot y, dot z, let's check how it looks like as a value. And let's think how we can use these value. Okay, so I have applied this attribute to points, so let's look at the points. And as I assumed, you only get value on y. That's assumable because the normal direction is y. So that's probably the direction we want to use as a scaling. So in order to create that scale axis, you can just create dot x, dot y, and dot z. Right. Now, and I would Also would like to make it normalized because I want to use it as an axis. And let's check how it looks like. And it says 0, 1 or -1, 0. Okay. The reason why we have one positive one or negative one is because based on the point position, if the point position is above the ground, could be positive. If it's at the underground, then that's negative. That's the reason. But all in all, I think the scaling is working. I mean, now that I have these 3 vector values, now what I want to do is to actually scale these particle position, which is at p plus force. Yeah, p plus force multiplied by strength. This is already being multiplied. So what I want to do is to scale these forces based on this axis, and you can just do it by multiply this by axis, and probably I would the thing is, I don't really want to have the negativity here, because if you have a negativity you get flipped. That's problematic actually, but let's try. And you also want to multiply this by some size of the scaling. Okay, let's see what happens. Okay, I know that this will be a problematic, but let's see. Okay, so everything is going above the ground, as I assume, because there is a negativity value here. So in order to avoid that, maybe I can just make the dot product as an absolute value, because I just want to get the magnitude or the length, not the directional information. There you go. Now you can scale it to the normal direction. Now this is not that interesting because you know in which direction you need to scale, so it's not that interesting. And there are some problem with this one as well, because x and z direction is being scaled by 0 in this case, so that's not good. Yeah, that's not good, so we need to fix that. So in order to fix that, let me see what I need to do. Yeah, this axis value is 0, 1, 0, which is problem. Yeah. But what I need is 1, 1, 1, and the middle y value should be controllable with these scale value. So in order to have that kind of value, I think I need to, this just multiplication doesn't really work. I mean with this one instead. Let me see. Okay, this might not. I could just say force multiplied by no, I mean force plus force multiplied by scale at the axis. Multiplied by scale. Does that work? Well, no. Actually, I don't like the result. I don't really like the result. When scale is equal to 0, I want to make the y-axis equal to 0, so that's not really what I want. Let me carefully look at what kind of value I have right now and see how I can use that. Oops. I'm just playing out with these values. This is really not the things that I did previously in order to create this setup, but just want to make it fun. Okay, so I have 0, 1, 0, so, and if I make it 0, so I think it does make sense to multiply with the scale parameters, but let me draw it down. So I have a direction, which is an axis, and I have, for example, like a geometry like this. And what I want to do is to scale these geometry based on this axis. Okay. To do that, right now what I have is this axis. Wait a minute, this is not really an axis, but this is a normal direction. Okay. And what I have done is, first of all, pick one of the points. Let's say this is the 0. I pick one of the point, created the vector, and normalized it to scale equal to 1. And then projected the wait a minute. I think I'm doing something wrong here. Yeah, or I have deconstructed the normal direction to x, y, and z, and then I projected this scale value. No, I have projected this normal value to this frame to get a component of this axis. But isn't it? Is this really necessary in terms of? Okay, let me check. Let me check with the more complex geometry. And what I would like to check is the difference between the axis and the normal direction. Right, so axis here, the normal direction here. Let me visualize it. So this is the axis information. Okay, doesn't really look like a normal direction. So I guess it does have some kind of a meaning. Right. Okay, yeah, it's related to the force value. But is that what I wanted? Is it really needed to relate it to the force field? I don't think so. I don't think so. No, I don't think it should be related to the force field, so probably I could just get the normal component x, y, and z and as it is. That's it. Okay, well, sorry for that. So I can just delete it. Alright, so starting from starting from the beginning. So this will be the axis, the normal direction itself. Okay, and you just want to scale the point position to that direction uniformly. So I'll just do the easy way, like I did some time ago. Okay, the one that I'm going to do, first of all, I'm going to make this normal direction fit onto a rotate this normal direction so that it will come to the x-axis. Then you could scale with just x-axis value, and then right after you have scaled it, you can rotate back to the original direction. That's it. Alright, easy as that. So to do that, you can get a rotational matrix by using a function called dihedral, which will create a rotational matrix from one vector to another vector. And in this case, one vector is normal, two vector is x-axis. Okay, then you're just going to rotate in this case force. And then you can now scale the x component with any parameter you want. Then you want to rotate back to the original. In order to rotate back, you need the invert matrix of this rotational matrix. So let's create another one by inverting the rot mat. Then rotate back the force. Alright, now you should be able to scale the force to the normal direction. And you just need to add this force to the point. Okay, it's a bit hard to see with these. I want to make sure that it works on simple geometry first. Okay, so by increasing the scale, okay, nothing happens. Am I using the right parameter? Seems like so. Nothing happens. Let's see why. Wait a minute. This is what is wrong. I need to put equal. Okay, so it looks flat. That is because the scale value is small. Okay, by increasing this value, you are scaling to the normal direction. Now, it's not that obvious because this is just a flat plane, so let's test it out with a pig head geometry. Let's make the scale a little bit bigger so that it might be easier to see. So in this case, the normal direction of this pig head is where? Yeah, to the normal of the surfaces. So what I would like to have is to scale these points to the normal direction. There you go. Okay, looks good. So this was a bit I don't know if this is good enough, but I wanted to try the other way but didn't work, so sorry for that. Okay, let's make the scale range from 0 to 1, 0 to 2. And I think I am good with these geometry or particle flow for now. Let's try to calculate the density and colorize it based on how dense the point is. So in order to do that, I do need a bunch of points to make it gradient. So let's make it 500,000 points. It's a lot of points. And let's calculate the density now. In order to calculate the density, it's pretty easy. You just need to look for each point, search for a certain area, and count how many points are there in these areas. And based on the number of points, you can see how dense this point is, that area. Okay, so let's use point wrangle again. Calculate density, and there are a bunch of functions you could use to search for closest points. I'm just gonna use the function called near points, and the parameter you need is the current point position, maximum distance, and maximum points number. So current point and distance and how many points to search as a maximum. Now I found out that maximum points in this specific density, the range with 100, the max point number to 100 and distance to 0.1 works, but I guess it really depends on the current density, so these should also be parameterized. Now after the search, you'll get a number of points stored inside this array, so you can now calculate the density, which can be normalized into 0 to 1 by just dividing the number of points by the maximum point number. And you want to make it float, so you need to convert one of the values, either this one or this one, to float in order to be able to divide to get the float value. Okay, as a result, if there is at least 1 point, you get at least 0.1 or 0.01 with this calculation. If there's 100 points in the distance of 0.1 as a radius, search distance as a 0.1, then you get 1 as a density, which is the highest density in this case. And let's apply this density to the attribute. Okay. I also would let's check the distribution of this density, so it's from 0 to 1. Right. And let's there is a chance that the density goes less than like 1, like 0.8, 0.6, or 0.4, something like that. If you increase this maximum point number to something really big, then you have a chance that you have a low maximum value. So in those cases, it might be a good idea to get what's the maximum value of this density. So I'm going to use the attribute promote to get the maximum value. Named as max density. Okay. Like that. Alright. Now it's time to try to color these points based on the density value. So I'm gonna make this ramp from attribute and use the density, and then you I need to change the range from 0 to the maximum density, so I'm going to set the maximum density value, retrieve from the detail attribute op input. Wait a minute. What was the name? Max density. Alright. And it might make sense to get the minimum density as well in order to get the gradation. So shall we have that as well? Let's create another attribute promote, rename this to minimum density, and then copy these to here and just rename this to minimum density, so you have a bit more contrast between the lower density and the maximum density. Now let's also change the color to something interesting like blue to make it look like an energy field. And when the density is really high, it could be white and have some accent with some red. Something like that. And probably I would like to make the grid size a bit bigger. These should be parameterized, I guess. Nice, looking nice. Now maybe a little bit more bigger. A little bit bigger, like that. And let me also change the color a little bit more. Okay. Now because of the density calculation, the setup becomes a bit slow here. because searching for the nearest points with a maximum of 100 points is pretty heavy duty. So if you don't want that, I mean, right now it's 1000, so make it 100, become a bit faster because you are searching for less points. But still, if you think it's still heavy, then you can decrease this distance. Something smaller will be a bit faster. And make the maximum point number to smaller value as well. Okay, starting to look nice. Now I would like to have additional value to control the color gradient, I guess. In this case, what I would like to have as an additional attribute to control the value is to fade out the energy field color from dark color to bright color from bottom to top. I guess based on the normal direction. Okay, so based on the normal direction, let's try to control these density color value. Okay, so how do we do that? How do we do that? It's not just about the y coordinate. I mean, in this case, this is y coordinate, but if you want to care about the normal direction, then you gotta think about something else, right? I mean, let's try with the y coordinate first and see how it looks like, because that's easier to implement. Okay, so in order to do that, let's get the bounding box information of this whole geometry. And then you get minimum y value and maximum y value. So let's create the normalized value for y from the lowest position to the highest position for current point position. So the point coordinate y is in between minimum y and maximum y, and then you want to normalize it to 0 to 1. Okay, and now I'm just going to multiply this value with when the bottom part is dark, the top part is bright, by multiplying it to the density. Now you get some gradations from bottom to top. And I would like to make it a bit more obvious to make darker on the bottom side, so let's create some darker color here, like that. Okay, so bad, not bad. Yeah, it's not bad at all. Okay, so let's see how it looks like with the pig head. Using the same logic, it comes from dark to bright on top. And actually this doesn't really look bad. Looks okay. Maybe I do want to change some steps here. Okay, but I guess I still want to try to create the gradient based on the normal direction other than using the bounding box information from bottom to top. So how do we do that? Now I just need to calculate the height from the base surface, right? So you just need to calculate the distance, the minimum distance between the current energy field point position to the surface, and then you'll get the value. Yeah, you get the value of that distance. And I also want to get the value if it's inside the geometry, inside the surface, which should be the negative value, and outside the surface, which will be the positive value. So in order to get that kind of information, I guess you could use a dot product again, right? So what I mean by that, you have a surface and you have some energy field like that, and what you want to get is the height at specific point. And if it's inside the surface, I mean, let's say this is the solid geometry. If it's inside the geometry, then I would like to make this negative. If it's outside the geometry, I want to make it positive, so on. So to get this kind of information, what I could do is to first of all project this point to the surface. As a result, you get the corresponding normal direction on that surface, on that point, right? And using this normal direction, and you can now project this vector from this point to this point. Let's call this A. Project this A to normal by using a dot product. As a result, you get a projected length, which is similar to this H. And because you are using dot product, if it's inside the surface, you get negative value, but also the size, the height. Okay, so that's the trick. And let's see. Let's do that. Let's calculate that. So, I guess I do like this bounding box information, so I'm gonna keep it so that I can switch between this and the normal based density. So, what's happened? I'm gonna call this Y, I'm gonna call this normal. And create a switch. And let's try to write down the things that I just sketched out. So, first of all, I'm just going to delete these. Okay, and what I would like to do, first of all, is to project this point position to the original surface to get the corresponding normal direction, as well as the projected point position. So, where this is the original surface, so I'm going to connect this to the second input, and then I'm going to use the function called xyz distance, which will give you a closest distance, which I'm not going to use it, but as well as the primitive number of the projected point, projected position, as well as the UV value of this primitive. So give empty primitive, give empty UV, which is going to be filled with this XYZ distance by projecting point position to prim and UV. Alright. Now, by having this two information, you can get a corresponding normal by using a function called primuv from the second input. As well as the projected position. Just gonna call it ppos. Like that. Alright. Now, I'm not sure if this is the normalized value, so let's make sure this is being normalized because I want to use it as a base vector to calculate the dot product. Okay. So let's calculate the height now. The height is equal to dot product between the normal and the current point position minus ppos. Okay. As a result, if it's outside the surface, you get positive height value. If it's negative, it means that the point is inside the surface, but you still get the size of the distance from the original point to the surface. Alright. And you don't really know what's the range of this height actually, so let's give it an h, a new attribute called h. Or do you know? I don't know. We don't really know what's the maximum of this h, so let's just give it as an attribute like that. And let's check how it looks like. So it's from 1.2 to minus 1.08. Okay, hopefully that's the height of the force field, I mean the energy field. So what I want to do is to I guess normalize this h value so that I can multiply with this density later. So in order to do that, you need to get the maximum value and maximum value of this attribute. So let's do that. Just like I did here, I'm just gonna copy these two set to node and rename this density with h. Just call this min h, maximum h. As a result, you get the detail attribute, which have maximum height information on the normal direction, to the normal direction. Now you can remap the h value and multiply it with the density. How do I call this? Density height weight. So first of all, we want to normalize the h value. So h, fit the h, and let's get the minimum h from the detail. Max h from the detail. And then min h, max h, and let's make it normalized like this. And finally, I am going to multiply this h to the density. Like that. Alright. And switch to 1. So hopefully the density has been gradient from inner side to the outer side. Let's see. And I'm not sure if this is obvious, so let's change the color inside to something vivid. like green. Okay. Yeah, it is changing. Ooh. Okay, well, it does look like it's working because where the green part is something that's inside the surface, and the blue part or the white part is somewhere outside the surface. So probably this is working, but I don't like this color, so I'm gonna make this back to black. Now I wonder which one looks better, the Y gradient or the normal base gradient. Each one has some strengths. Can't decide. Okay, I think it also depends on the size of the points. Right now I am using, which one? Display sprites. If I use pixels, nice. I don't know if you can see it through a live stream quality, but looks nice with the pixel view. Yeah, much better. Alright. Huh. Like a smoke. Yeah, I love it. If I switch this to 1, 0, now in this case, the second one looks better, I guess. If I change the black color to something bright, okay. It does change a lot of characters. Purple looks nice. Darker color looks nice. This is nice. It looks like a film-like surface. Keep it black. Love it. Okay. And of course can be animated. Let me try with the grid again. More like a wave, I guess. Okay, now this could work with any number of frames because I have procedurally used end frame inside Wrangle. So if you just want to have a loop animation with the 60 frames, you just change this one and that's it. It still loops. Right? Cool. Let's change this back to pig head. Let me try to see in real time by caching it. File cache. Okay. Interesting. Maybe a bit too fast, but works. Alright, so that's pretty much it for what I wanted to do today. Was sorry for the late notice to do the live stream, but the process itself is pretty simple, as you can see here. So just a simple idea using periodic noise as well as some density calculation plus some normal directional scale, and that's it. Okay, if you have any questions or feedback, please let me know. Meanwhile, I'm going to store all the parameters that I could control to this controller. Just by drag and drop. So, starting from energy field. Noise speed. Size. Periodic size. Strength. That's particle. Let's just call this spread. Scale. What was this? Oh yeah. Normal direction scale value. So. Right. So these could be shared. So the density related value, this is the distance, right? So density search distance, density search distance. Oops. Density search max point. Max point. And I could copy this to here as well. Copy this to here as well. What else? This switch. How do I call this? Density type. Density gradient type. Either 0 or 1. Okay. That is pretty much, and maybe I can also bring this color map to the parameter. Right. Okay, so now I can control everything inside this controller. Shall we try out? Like, oops, this is cached one. So if I increase the spread, looks more dissolved. If you have less value, you have more like a bubble-like shape, which is still interesting. What else? You have speed, which is the parameter for the animation speed. So if you have high value, it's gonna be faster. Okay. The periodic size is how many patterns you have on how many periodic patterns you have. The bigger you have, the one pattern is going to be really big. Smaller, you get repeated pattern again and again. Like if you make it 2, you see some repeated patterns all over the place. Now that's also interesting. I'm gonna keep it to 20, but big enough to make it unique. Particle spread, yeah, I did try it out. Normal scale, scale it to the normal direction. Making it 0 also looks interesting. It looks like a water surface somehow. Interesting. Interesting. In this case, I don't know what it is, but nice. Density search distance, if you increase it, you change how you calculate the density. So lower those both value is, you get faster result. So maybe you want to make it lower as possible to get the nice image, to make the calculation faster. And rest, just change the gradient type. Now this is pretty obvious, the difference. Both ways, nice. Okay, that's pretty much it. You can torus, yes, let's try that. Thanks for the comment. Torus. Let's set the size of the torus to be pretty much the same size as these. Something like that. Let's make it smooth. Switch it to the torus shape by changing this shape to 2. Alright. Donut. Some venom-like donut. Alright. Interesting. Alright. Looks nice. I like the color a lot. Yeah, it looks like a ghost. Good for Halloween, yes. Yeah, definitely. Okay, so that's pretty much it for today, I think. Thank you very much for watching, and thank you very much for the comments, everybody. I'm just gonna end the live now. As always, I'm going to upload the files to a GitHub, and you can download the file from video description page of this YouTube live stream after the live. And you can also download the file from Patreon page of myself, which you can find the link on the same video description page. So if you're interested, please visit. And that's it for today. Thank you very much, and thanks for all the comments. Good night. It's 5 a.m. in Japan time. I should go to sleep. Good night, everybody. And see you sometime next week. I don't know when I can do the live.